Hello again. This is Roger Kochbar for the Bioelectricity course. We're in week 7, and this is lecture segment number 4. In the previous segment, we looked at a recording that was a real experimental recording between two fingers, one finger on each arm, on each hand. It was a complicated tracing. To understand the origin of traces like that, which is the focus of our course, to understand the principle by which things happen, it's now useful to go and look at what happens more or less at the other extreme. Suppose we have just a single fiber. What extracellular signals does it create? Let's just look and see, taking advantage of the power of simulation. Our goal here is not so much to give an explanation of what we see as, right now, just to take a look at the waveforms that are observed. So let's proceed in a way that is similar to what we have done in earlier weeks of the course. Let's suppose that we have a fiber, single fiber, uniform, so it has the most simple structure. Let's suppose we have one stimulator, which I've designated R, and it's over here towards the left end of the fiber. Let's suppose that we have two electrodes, one here, one here. And we actually have a pair of electrodes. One electrode is a penetrating electrode, will tell us the transmembrane voltage. The other electrode is an electrode outside the fiber, which will tell us the voltage outside relative to a reference that's a long distance away. We can use this setup to give us some useful information as to what is expected. Suppose we now use this arrangement and apply stimulus. Here's our stimulus waveform, so it's all the way down to the left, a 400 microsecond duration stimulus. And here's our amplitude, which we know from earlier weeks of the course is about twice threshold. So it should originate action potentials, and as we know from the week on propagation, they should proceed down the fiber. And indeed, here they are. On the top trace, we have the waveforms versus time going this way. And these are transmembrane waveforms. Transmembrane. Here it is on the left, and here it is on the right. These are very familiar action potentials because of our previous work. Now, what happens outside the fiber? If we look at our two electrodes outside the fiber, we again see two simple waveforms, but they are quite different. Here's the waveform that's outside near the left end. And here's the waveform that's outside somewhat further on down the fiber. We look at these waveforms, you'd say, they do seem to have some similar characteristics. They are displaced in time, one from the other. So there's this time interval between corresponding points that corresponds on the extracellular pretty well to what we see on the intracellular. So the extracellular reflects timing information just like the intracellular does, but the wave shape is pretty much altogether different. So that on the intracellular trace, essentially it goes up, comes back down. It does go down below the baseline for a period of time, but to a first approximation, you'd say this is a pulse, a positive going pulse of the inside with respect to the outside. On the other hand, if we look at the extracellular waveform, we'd say, well, now, this extracellular waveform, it's biphasic. First it goes up, then it comes down. Then it does this little wiggle over at the end. This biphasic nature is characteristic of what you see in extracellular waveforms. Usually the first phase is positive. Usually the second phase is negative. In a temporal sense, you would say what we're seeing here is we're seeing the excitation wave get closer to the electrode. So as the excitation wave approaches, we see this positive part. As the excitation wave moves on past and we're on the back side, we see the negative part. This is the departing excitation wave. That is to say, it moves further on down the fiber. There's another item of nomenclature that's also important. This portion of the extracellular waveform, where it goes from the positive to the negative, this is called the intrinsic deflection. I suppose intrinsic means it's within the middle of the waveform, but that's the name that's used for it, the intrinsic deflection. There it is right there. The thing about the intrinsic deflection is that there is a close time correspondence between the time of the intrinsic deflection and the time of the midpoint of the action potential. So if you make a vertical time bar here, you'd say we can use the time of the intrinsic deflection to tell us about the action potential underneath. The action potential underneath will be about halfway through its rise at the time when the intrinsic deflection is about halfway through its fall. These timing correspondences can be very useful in mapping out the sequence of events that are happening in the tissue underneath the extracellular electrode without ever having to penetrate the tissue to get a transmembrane potential recording. And finally, let me make note of just one additional point. We do have these little squiggles here. So here are these little squiggles at the end. Those are smaller, and they reflect repolarization. The changes in the waveform at the end of the action potential. It's interesting how on these traces we actually see the end of the action potential and repolarization more noticeably here on the extracellular than we do there on the action potential. But that's where they're coming from. And finally, I should note the magnitudes of the signals. Because of the way the graph is scaled, when you look at them here, they seem to be about the same. But when we look at the actual numbers, 60 and minus 60, we're on a scale here, a vertical scale, of 120 millivolts. In contrast, on the extracellular trace, we have 0.015, 0.015. These are in millivolts. So now this is just 30 microvolts. We might say the scale is, maybe 1/100th as great for extracellular as for intracellular. So that means that's okay, because on the one hand, with a computer it's easy, and with instrumentation it still is fairly easy. We just have to turn up the amplification, and then we can see the signal just fine. The only caution is that when we turn up the amplification, we're also going to see all the interfering signals better too. That is to say, we increase our sensitivity to noise, as we were talking about earlier. For this slide, there is no noise, so what we're observing is simply that the amplitude is much smaller on the extracellular side. Well, our carving is frowning at that news. It is a problem, and so you do have to ponder it and figure out what to do about it. Thank you for watching this segment. We'll be back in a little bit and talk about it some more.